So in our next lab, we're going to use a technique of spectrophotometry, which utilizes a spectrophotometer. Imagine that, okay, boys and girls. And in this piece of equipment, or in this concept, what we're looking to do is utilize our understanding of why some chemicals or some chemical species have color. Now, we've already set the stage in other lectures why transitional elements, okay, make color. And real quickly, to reinforce this idea, transitional elements, okay, make colored solutions. And the basis for that is they make complex ion. Transitional elements tend to have multiple oxidation states where they lose more than one electron. The example I was giving in class is iron plus 2, iron plus 3. And these two elements, or these ions, have become these ions due to the fact that they can lose electrons in different orbitals. And that opens the door for them to be really positively charged. And of course, having a large positive charge gives them the ability to attract the negative end of the polar water molecule. So much so, this polar molecule just doesn't attract, it actually goes into and possibly enters the orbitals of the iron that are outward facing the nucleus. So these water molecules are so attracted, they impinge on the orbitals on the outside edge of this ion. And why are they so attracted? Well, for reasons we've explained for the millionth time, Coulomb's law, the force of electrostatic attraction, is equal to the size of the charges, R1, R2, over the distance squared. And I have to keep mentioning this because it's so most important part of our class is talking about electrostatic attractions. So having a larger charge, because you can lose more than one electron, as in the case of many transitional elements, and by losing multiple electrons, as most metals can do, or at least losing electrons is what defines a metal, the size of the ion gets smaller because the remaining protons can pull in the other electrons. So by making our distance smaller and the charge higher, this force of attraction is so great that, again, it pulls water molecules, okay, essentially into the atom. And some people would suggest that these types of interactions are covalent bonds. Now, they make something called complexes to show that these aren't random water molecules. For instance, the iron molecule, again, iron plus 3 would be the center, and it would have 6 ligands. It would have actually, and I'll just draw it like this, it would actually have 6 water molecules. Again, the oxygen end, the more electronegative end, is what's going to stick outward, okay, or that's the one that's going to be impinging, and I'm not going to draw all of them, but you're going to have 6. Well, why 6? Because only 6 can fit. And we draw this structure, at least chemically, as Fe, 6 water molecules, subscript 6, brackets to show it's sticking together as some sort of molecule. And the whole thing is plus 3 because water is neutral. Okay? So that is how we would draw the complex. So we draw it as a complex, again, because it's as if it's a bonded molecule. So, what's so important about this? Well, as we've talked about, because of crystal field theory, the idea that these lone pair of electrons in the oxygen start impeding on d orbitals, some of them, not all of them, they split the d's into 2 different energy levels. So much so that, well, at least they split it just enough so that the photons of light can energize electrons to move from one to the other. And that little gap allows these chemicals to absorb wavelengths of visible light. If the gaps were too small, you would need a lot lower energy than visible light, and that wouldn't work. If the gaps were too big between the two orbitals, you would need something more energetic than light. So it's important that these gaps between the d orbitals, okay, that split, are just small enough to absorb visible light. And that means that if we've got a colored solution, it's due to the splitting of the d orbitals due to the oxygen's lone pairs that are, again, being pulled in because of Coulomb's law. So that creates the color. And again, the reasoning behind that is if we absorb part of the spectrum of white light by definition has all the different photons and wavelengths of light, and we use only exactly this energy that takes an electron from one lower d orbital to a d orbital that has what? Has some electron-electron interactions with the water, okay, and become destabilized and get higher in energy. If electrons can jump, they get excited. They're going to use some photon of wavelength of light from the entire spectrum. And if they're going to use it for this electron to move up, then what you see essentially is what's not being used. And this is called an absorption spectrum. All right. Now, how does spectrophotometry work? Well, what we're going to do in this lab is we're going to use a device that's going to measure the essentially missing wavelengths of light. And how it does that is this. It's going to take basically a source, okay, of light, and it's going to essentially shoot that source onto something called a cuvette. So we have this spectrophotometer, and it has an internal light, and it basically has a full spectrum. It has, now for those who don't know, a full spectrum means that every single individual wavelength, and the wavelength is the length of the wave, and we should know that the longer waves are usually the red region of the Roy G. Biv, and the shorter waves are in the violet region. So the different colors of visible light are associated with the different wavelengths. That's important. Shorter the wavelength is from the start of a wave to the start of a new wave. Okay, so this is a wavelength, this is a wavelength. You can see that the wavelength for the red is longer and for the violet shorter. Okay, so the size of the wavelength is related to the energy. The violet has the higher energy and the red has the lower energy. And that's really important because the type of colors we see, like in transitional solutions, are dependent upon the size of the gap that's split in the D's. Bigger the gap, that means you're going to need a light from are going to need a photon of light or a wavelength that's higher in energy, which means you're going to start using more of the blue and the violet end of the spectrum. Don't forget the Roy G. Biv that you may have learned kind of shows that, the longer wavelengths to the shorter wavelengths of light. So this is the higher energy, which would require a what? A bigger gap in between the D levels, and this is a lower energy, longer wavelengths. Okay, and again, those photons would have to be shorter. So again, our color changes that we have are dependent upon the types of gaps that we produce. And again, I know I keep going down that road of crystal field theory, but it's really important that you have a good solid foundation. Okay, so back to the spectrophotometer. I'm going to shoot light that has all of the wavelengths through the RGB spectrum. Okay, and essentially, and I'm simplifying this a little bit, but it still works. This cuvette is a container that we put liquid or some kind of solution in. Okay, so it's got these, possibly these complexes. If I have, let's say, the iron complex that I just put in here, it's got some color associated. Now, we're going to have a beam of light hit the cuvette, that's basically a plastic container that has the solution, and this beam has all the wavelengths, and then the beam that comes after it that hits a detector, okay, is going to be less if there's something in here to absorb that light. So this light, okay, with all the different wavelengths of light, hits this cuvette with a chemical who's using part of the spectrum, and what it doesn't use is the light we see. That's the concept we're using here, okay? And the light that comes out, this is the transmitted, they call it the transmitted um, light wave that leaves the cuvette to a detector. So we're shooting light through the cuvette, okay? This is called the incident light. Remember, this is my light, kind of like a flashlight here, and it's giving off photons of light, all different wavelengths, okay? And we call this the incident wave, I0, and this is the transmitted, okay, um, light that wave or ray that comes out. So I like to think of it as this is the total, the IO, the incident, and the transmitted, of course, is the part. And if you think of what that means is part over total times 100, you can get yourself a percent of transmittance, okay? So what we do is that essentially we shoot light, and the light that leaves the cuvette is going to be lowered if this cuvette has something in it that's absorbing that wavelength. So we shoot light and or wavelengths of a certain light, and there's less of it coming out because this chemical is using it. And of course, what that means is electrons from lower energy levels are jumping to levels that are higher in energy. That's what that means. And that exact amount of energy jump from one to the other is what's being utilized. And that's what the wavelength of light or the photon of light, how it's being used. Now it's really a frequency, but certainly we can use the wavelength idea. So what does this mean? Well, it means that I can take this total, which is the incident, IO, the part is the transmittance, and I can get a value here. Now, let's put some numbers. Let's pretend that the IO is 10 to make life easy, and I have a very dilute concentration of some kind of chemical that has a color that's using part of the spectrum of light. And so we would say that, okay, if this came out on this side, let's say 8, okay, then we would say there is approximately 0.8, or if we times it by 100, 80% transmittance. Wow, 80% transmittance would mean that that's a lot of light leaving the cuvette. There isn't a lot of loss. The loss would be 2, right? If this is 10, and then you're measuring 8 coming on the detector here, you lost a value of 2. Why? Because this absorbed what? It absorbed 2. Okay, and that would be in a dilute sense. Now, if I have a more concentrated sample, all right, a more concentrated sample, then again, I still have the same transmittant ray over the incident ray, okay? And let's do it this time. Now let's say 10 is still the brightness or luminous of the light. That's a 10. And let's just say now it goes down to 4. So that's going to be 0.4, or if we times it by 100, we get 40% transmittance. What does that mean? Well, the transmittant ray is lowered. Why? Because there are what? More chemicals in the cuvette that are doing what? Absorbing more of that certain wavelength of light that's making the electron jump. So party people, as the transmittance number decreases, that means you have more molecules, or in this case, complex ions, that are doing more absorption because there's more of them. And there's that word absorption. So it's kind of an inverse relationship. As this number goes down to 4 or 3 and 2, clearly the stuff inside here, there's more of it, therefore it can use more of the light. So as this becomes a darker color, higher concentration, okay, there is more of those complexes and your transmittance would go down. This ray drops. So that would mean that the chemical is doing what? Absorbing more. So because it's an inverse relationship, here's what they do. They measure A for absorbance, and absorbance means how much this chemical is absorbing. If we're going from 10 to 4, this is absorbing a unit of, let's say, 6, right? And if this was 10 to 8, this was absorbing a unit of 2. So that the absorbance goes up of the chemical as the transmittance drops. So what they did is to fix this is they made that absorbance, how much the chemical in the cuvette actually absorbs and takes up, okay, is equal to the negative log of the transmittance. What? Of course. Why would I do negative log? As this thing is becoming a smaller, what? A smaller number. What's 4 out of 10? It's 0.4. Now, I just made that up, but these numbers can be much, much smaller. So what does this mean? This negative log just allows me to take a number that's getting smaller by a large amount. Even though I write in 4 over 10, these numbers can get even smaller, 0.01, 0.001, 0.001. So as a transmittance, 0.001, here we go. So as a transmittance gets smaller, okay, this number gets too tiny. By putting this into a base 10 log, right, this is going to be 10 to the negative 2, right, 10 to the negative 2. By putting a negative in front, negative log means that just like our acid-base way of using it, it just makes this into an exponent, which would be 2 base 10. And I'm putting a what? A positive in front because I'm getting rid of the negative sign. The negative sign is that these are small numbers. So a negative on a negative exponent makes a positive. This would be what? 3, and this would be 4. And in this way, as a transmittance decreases, the value decreases, which means what? The transmitting ray gets smaller. That means there's more what? A, and that's how that works. The A increases as a transmittance goes down. So that's why they use that. So all you really have to know is that as this gets more concentrated, the absorbance increases, and that's Beer's law. Very simple. If I've got a solution who has color, and if I've got a higher molarity, okay, it's going to be able to absorb more wavelengths of light. If I've got a dilute, less concentrated, a lower molarity solution of the same compound, it's going to have, all right, a lower absorbance. Therefore, the transmittance is higher. It's an inverse relationship. Okay, so let's talk about the lab. So the lab, my friends, in chemistry is about trying to find the percent by mass of copper in the what? In a alloy of brass. So what we're going to have is we're going to have copper. We're going to have copper, copper, copper. This is a what? Probably a face center cubic structure. And then we'll have some copper, and then probably somewhere in here we're going to have some zinc. Now zinc has about the same size as copper, so this is a substitutional alloy. All right, so this is all a crystal, and we're trying to figure out the percent by mass of copper. So what's cool about this is that we're going to be able to, we could just oxidize zinc and not copper using different oxidizing agents, but we can't do that because the crystal's three-dimensional and we're going to have some zinc inside. So what we're going to do is we're going to take some nitric acid and we're going to basically drive all of these or oxidize all of these solids into aqueous ions. So nitric acid, and the reason why we're using nitric acid because the nitrate ion will oxidize the copper. We're going to make copper +2 and zinc +2 ions in solution. So we're going to have a solution. So we're going to use some nitric acid to make that. All right. Now, what we're going to do is essentially we're going to put this solution into a cuvette that we just talked about, and we're going to measure the absorbance. And I know the absorbance, okay, is proportional to the concentration, which is molarity. So I'm going to measure this A, and somehow I'm going to be able to get the concentration of it. So that's what this is about. Now, the problem in this scenario is that we can't just simply put it into a computer to measure the absorbance because we know the relationship is A, okay, is equal to the concentration, but there are other factors involved. Okay, for instance, the light has to pass pass through the width of a cuvette, which is approximately 1 centimeter. So we say A is equal to B times C. Now B is 1 centimeter. C is the molarity, and then we have some constant called the molar absorptivity constant that we would have to use. So this is a formula here that's given to us in our reference table that can help us use this. If we want the concentration, if we have the absorbance and we have this and the path length, we could solve for it algebraically. But that's not exactly how this lab's going to go. So please pay attention because it's really important for the homework. So let me just make some room here. Okay? What we're going to do is take our computer and we're going to calibrate it. Calibrate the spectrophotometer. Now what I mean by that is the spectrophotometer is going to measure absorbance, but it's not going to know what the concentration of the compound is. So we're going to actually make something called a linear regression line. And let me explain. So what we're going to do is we're going to take the spectrophotometer and we're going to plot concentration, or these brackets works for me, and absorbance. And what we're going to do is we're going to make a set of stock solutions that we definitely know the concentration in. Okay, so let's make some up here. Let's make this, I'm just making some numbers up. Let's make this, let's see, 2 molar, 1 molar. Let's make it 1 molar. We'll do 1.5. 1 molar, and then 0.5, and I'll make it 0. So that'll be my 0.5 line, my 1 line, 1.5, and 2. Okay, I probably should have put that outside. All right, and so what we're going to do is we're going to make these solutions and know them for certain, and then we're going to put them in the spectrophotometer. Now, the more concentrated, okay, of the stock solutions will wind up having a higher absorbance for reasons we've just explained. And as the concentrations decrease, so will the what? Absorbance. There's less of them there. So we're going to plot this, and it should come out to be a straight line, okay? And if not, we're going to hit a regression button, and we're going to do a regression best fit that goes through these lines. And it's going to give me a slope for this, and using linear algebra, I know y is equal to mx plus b. The y, my friends, is the absorbance, right? The x is the concentration. So think with me for a second. C, which is the y, I'm sorry, my bad, the A is your y-axis, absorbance, is equal to the slope, which they're going to give you that, times the x, which is the concentration, plus if they give you the value for b. If this line goes through the origin, it'll be 0, but plus b possibly. So you're going to have this value the computer's going to read. The computer's going to give you the slope, and it's going to give you the y-intercept, and you're going to solve for your x, which basically is the computer is going to read where on this line do you have a concentration. So if you measure an absorbance, let's say right here, it's going to read the concentration right here. And that's how we actually use the spectrophotometer. We're going to calibrate and make this line first. It's called a Beer's law line, okay? And that's what we're doing. So it's a Beer's graph, a calibration curve, okay? And that's what we do. So essentially, we're going to make 4 stock solutions or more. We're going to hit the absorbance. We're going to measure the decreasing absorbance with concentration. We're going to make a linear regression line, and then we're going to use that to solve for the concentration of the what? The resulting solution that I made by adding nitric acid. So I'm going to take basically brass shot, and I'm going to put it in a container. I'm going to add nitric acid, and you're going to see the reddish-brown gas in a fume hood. It's going to dissolve it. We're going to basically take the remnants of the dissolved copper +2 and zinc +2, which, by the way, has no color, okay? And then we're going to put that in a volumetric flask. So we're going to take all of these and wash it through. And this is a volumetric flask that's going to be measured at 100 milliliters. And so we're going to make 100 milliliters of this solution. So we know it's 100 milliliters. We know the what. We're going to take this and pour this into a cuvette, as we just talked about, into a spectrophotometer. It's going to read the absorbance. We're going to use our relationship of our calibration line here. We're going to solve for the what? The molarity of the compound. And I'm going to have the volume and the molarity. And my friends in chemistry, that's going to give us the moles. And with the moles, okay, I can convert to grams, and I can get grams of copper. Knowing the initial grams of the brass alloy, I can figure out how much is made of zinc and copper. Pretty darn cool. All right, so if you want to, you're going to see that the worksheet below is just a application of this process. We look at number 5, and this is question 5 of 2006 AP Chemistry. What they're doing here is talking about what would be the optimum wavelength. When we do this experiment in our lab, we're going to first put a solution of copper, and it doesn't matter which one, into the spectrophotometer, and the spectrophotometer is going to measure all the wavelengths of light that complex of copper and water actually absorbs. And we're going to pick the highest peak because we want to set and calibrate or tune our spectrophotometer to only measure the what? The wavelength of light that the compound best absorbs. Remember, there's a lot of electrons that can exist in this compound. We want the electrons that are best absorbed from a certain wavelength. So if I look at this peak, I want the top part of the peak. This shows me there's maximum absorption at a certain wavelength, which represents a certain energy, which represents the energy needed for electron to go from one to the other. If you think with me, if this is maximum absorption, this is probably going to be the smallest gap here. Okay, well, we can think of it that way too. In any case, so this question is just like we're going to do in our lab. We're going to find the peak that it best absorbs, and then we're going to set our spectrophotometer to here. So this is 440, this is 460. It looks like it's halfway in between. So approximately 450 nanometers long is the wavelength of light, or the photon of light with a certain energy and color, that this chemical actually absorbs the best. That's it. So the optimum wavelength is 450 nanometers. Why? Because it's the best, this chemical best absorbs that wavelength, so we'll get the best data. Okay, it's just that simple. Now, B is the calibration plot that we talked about just now. So these absorbent values that you see here are nothing more from putting known solutions into the spectrophotometer and measuring the absorption. So that's that. So we're going to have to make a curve. Now, our computer will lay this out, but I'm asking you, or at least the AP was asking to do this. So here's our concentration. So if you notice, our values here are all times 10 to the negative 4. So we can actually just use these other numbers right here. So it's going to basically 0 through 18 scale times 10 to the negative 4. So this is a 2-point question here. They want you to indicate the scale on the horizontal axis. Well, if I think about this for a second, 1, 3, 6, 9, 12, 15, okay? Of course, that's times 10 to the negative 4. Okay, I can do that. If you're not comfortable with that, you can go 3.0 times 10 to the negative 4 and put it there, 6.0. You get my point there. Okay, and then basically what you're going to do is you're going to take the known concentrations, because the computer doesn't read concentrations, it reads absorbance. But by putting in known concentrations and now reading the absorbance, we just plot these values. Of course, the more concentrated is going to have the highest absorbance. So when you plot this, you get something, and I'm just going to quickly put these in here. This might not be completely accurate, but you get the drift here. So I'm just putting in the values that that these basically represent. All right, and the best that I can. All right, so I've got my points here. And then what you do is you draw a best fit line between them. It won't be perfect, and I certainly am not. Okay, So I do a best fit line. So they give you a point for the appropriate scale, okay, by labeling it with appropriate values. Of course, this is the concentration of uh, the iron cyanide complex. Okay, it's a molarity. All right, so that's 2 points there. Now, Captain says solution of unknown concentration has an absorbance of 0.3. So this is kind of like what? Now that you have calibrated this, now you're taking some unknown concentration, kind of like what we're doing with the brass lab, where we're dissolving all the brass, and now we're going to make a solution of it. I want to know its concentration. So basically, we take an unknown amount and we put it through the spectrophotometer, and we get what? Well, we get 0.3. And essentially, we hit this line here, and then we read down. Now, my line is terrible, okay? If you use the data carefully, you actually will get closer to a 16. So this will be 16 times 10 to the negative 4, and it's an absorbance. Absorbance has no units. And you say, well, why doesn't it have any units? Because isn't it a ratio of light entering and light leaving, right? It's a ratio of the light entering and light leaving. So whatever unit you give for light would go by the wayside. So there's no units there. Any case, that's how I would do that. Write the equilibrium expression. We haven't done a lot of this, but I left it anyway because it's a lot of fun. Kc is like any Kq. It's what? Products over reactants. The product is FeSCN plus 2. Products over reactants. Notice I'm putting them in brackets to show concentration, because the changing concentration is tied to spontaneity. And that's all you're doing. Products over reactants, coefficients become exponents. These are all 1. And then solids and liquids don't apply, so therefore these all have a molarity. So that's simple. Okay, and if you didn't quite get that, not liking that, we'll do plenty of that later in the year. D, if the student's equilibrium value for solution, remember, you're solving for equilibrium based on these values. So if the student's equilibrium solution of the product over the reactant, okay, fades to a lighter color, what does that mean? That means there's less stuff in the cuvette. It's less concentrated. Hey, there's less stuff. The molarity is going to drop. Before the student measures the absorption, will the calculated value of Kc be too high? So if the stuff is fading before you can measure it, that means the concentration is going to be lowered. Remember, absorbance is related to concentration. Lower the concentration, the less stuff there is to absorb the light that comes in. So the absorbance drops. So you would say the value of Kc would be too low, essentially because the fading color represents less product or less moles of the compound. Therefore, the concentration drops, which subsequently makes your Kc or Kq drop in the equation above. Very simple. E, probably the hardest question. Calculate the molal absorbency constant. Remember, even though we're using a graph in our lab, we also have this formula, A equals ABC. Well, in part B, we found that we had a value of the absorbance of the compound, the unknown, to be 0.30. The A is the constant we're looking for. B is the path length. That's the length of the cuvette the light had to travel. I'm telling you it's 1.0 centimeters, so it's timesing it approximately by 1. That's a hard thing. And then I'm timesing it by the concentration. Well, we know the concentration wound up being, if you do the curve better, 16 times 10 to the negative 4. And this concentration is molarity. So if I rewrite this and solve for A, okay, A is going to equal 0.300, has no unit absorbance, okay, over 1.0 centimeter times 16 times 10 to the negative 4 molar. And you put that in your calculator, and you get 188, and you get a point for that number. And what's the unit? Well, there's 1 over centimeter and 1 over molarity. You solve for A, right? If I rearrange this, A is going to equal big A over BC. It's just algebra. So 1 over the path length, 1 over the milliliter. Now, if you want to be fancy, you could write 188, pinky up, centimeter -1, molarity -1. It's another way of saying 1 over. Okay, and that is the constant, which is kind of cool because now that you have the constant, all you do is put the spectrophotometer or the cuvette of your unknown into the spectrophotometer, read the absorbance. You know this is 1. All you got to do, okay, is solve for the concentration. Another way to do it. So you can see these problems that use this formula, which by the way is given to you and the parts of it in your reference table. Okay, that was a killer longer lecture than I wanted to do, but hey, I feel bad now I'm over it. Okay, hope that helped in some small way.